Hello again. We are back from the break. And before the break, we talked about the concept of normal or support force. Any object touching any other object, obviously, there are force interaction between them. In the case of an object sitting on a table, we had force of gravity pushing down on the table and force of support force or normal force by the table is pushing up on that object. Another concept that we're going to talk about is equilibrium. What do we mean by equilibrium? When objects are under influence of forces can be in the state of equilibrium, even though there are forces acting on those objects. For example, looking at these painters on a scaffold, they are kind of tied with two ropes on the roof, and they're standing on the scaffold. They each has weight, so there's a force of gravity that for each one of them. And the scaffold itself also has a force or weight, force of gravity. And these forces are pushing downward. And then we have a force or tension on these ropes that are actually pushing upward. So if we are looking at all the forces that are involved here, this is the weight of the big guy, and this is the weight of the skinny guy, and then this is the weight of the scaffold board. Now, these forces acting downward due to gravity. So what is countering that? The tension on this on this rope, and the tension on that rope. And notice that these tensions are different depending on where these forces are located. So if more forces are located on this side, therefore the tension on this rope would be larger. But the scaffold is not moving, and so therefore all of these components here, the force components are kind of balancing each other, so there is no net force. So net force is zero in this case. And we can say that this system is under equilibrium. And it's under static equilibrium. In other words, it's not moving. Whenever the net force is zero, the system or objects that many forces are involved in it, they could be in a state of equilibrium. There are many examples of that. And as you can see in this picture, we have many cases that forces are all balancing each other, all the forces downward and all forces upward, to the right and to the left. They're all balancing each other, and these objects are on static equilibrium. So, for example, if you do a tug of war, and if both forces in both directions are the same, that system is in a static equilibrium. Now, we have another type of equilibrium, which is called dynamic equilibrium. And the condition for dynamic equilibrium is also when the net force is zero. However, the object could be moving at a uniform, constant velocity. It could be moving at constant velocity and still be in dynamic equilibrium. For example, you're on the conveyor belt here, and you're moving at the 3-4 meter per second. Is a constant speed. So you are actually at dynamic equilibrium. The train is going at the constant speed straight, and there is no net force. All the forces that are acting on that train balance out, and this train is moving at, say, 150 miles per hour. That is at dynamic equilibrium. So dynamic equilibrium and both static equilibrium, the condition is the net force should be zero. One question is that a bowling ball is equilibrium? When would that be? Well, obviously when it's at rest, it's at equilibrium. But when it's moving steadily in a straight line path, it also could be at equilibrium. This equilibrium is dynamic equilibrium, and this one is static equilibrium. So both of these are correct. So you are pushing a cart at the steady speed in a straight line. If the friction force is 70 Newton, how much force must you apply? The key word here is a steady speed, straight line. So that means a constant velocity. So that means you have to have a net force which is zero. So when can you have a net force that is zero? Is when this force is also 70 Newton. You are pushing a cart at rest until it starts to moving in a straight line. Now, if the friction is 70 Newton, how much force must you apply? Here, the cart or object is at rest. So you need to apply a force which is a little bit more than the friction force. Because if you apply a force, there is a friction force, F, and there is a applied force, which you apply this way, F. If they are equal, this cart will not move because they just balance out. Because it's sitting at rest, it's going to stay at rest. However, if you add a little bit of a force to this, then you set this in motion. You need to add a little bit more force than 70 to get it moving at a straight line. Now, we're not saying constant velocity, but get it to move. Once it starts moving, then what happens? Then you don't have to add that little force anymore, because if you do that, then you have a net force to the right, and this thing gonna accelerate. Then you cut back to the original force, which is F, and at that point, you're going to have this car to move at a uniform velocity. So you see how that happens? Because you need a little bit more force to get this to move. So that's called static friction. Static friction is a little bit more than the dynamic friction. I'm going to talk about that in a minute. But before that, let's answer this question. This has to do with the support force. Suppose rather than standing on one scale on your bathroom, you have two scales, and you just stand kind of balanced 2 foot on two scales. What would be your weight? What would your weight be reading on each one? Is it going to read your full weight? It's going to weigh half of your weight, because now your weight is distributed on 2 foot on two scales. So each one add together, you get the full weight. Because what you push down on the scale wants to push back at you. The support force, which actually what you read on the scale, is half of your weight on one scale, half of your weight on the other scale. Another important application of gravitational pull is when we do a free fall. When you have an object dropped from a height, that object is going to free fall towards the earth, towards the center of the earth. Of course, it's going to hit the surface of the earth, okay? But until that point, it's going to have to free fall, provided that we ignore the air resistance, the air drag, because there's a lot of resistance due to the air. If you want to feel the air resistance next time you're driving your car in somewhere that is not that crowded, just open your window up and put your hand out of the window a little bit, and you can feel your hand is being pushed back by the air. So that is the air drag. the atmosphere, molecules in the atmosphere is actually acting on your hand. So there is a friction due to the air. So now we ignore that in free fall. We say that there's no atmosphere, and then you drop something, it's going to pull down by the earth. So it's going to accelerate because now you have a constant acceleration. And that constant acceleration we already talked about is G, 9.8 meter per second squared. Okay? So we remember that Galileo demonstrated that no matter how massive or how light an object is, they're both going to fall at the same rate. Okay, provided we ignore the air resistance, because air resistance would affect the larger object more than the small object. The concept of gravity or acceleration due to gravity, as we said, is not going to discriminate against one object or another, because the ratio of the force to the mass is always constant, and that's G. G is equal to F over M, just like the ratio of the circumference of the circle to its diameter. So if you have a small circle diameter, and this is circumference, and you have a large circle with the diameter larger and larger circumference, the ratio of this is always pi. Then the same thing happens here when you look at the ratio of the gravitational force to the mass of an object. Now let's look at what happens to a free fall for an object and how far of a distance it would cover each second. You go up on a cliff and you drop an object. And then at every second, you measure its distance. Starting at 0 second, you have, let's say this is your reference, is 0. And then at 1 second, you see that it's 4.9 meter down, almost 5. At 2 second is 19.6. At 3 second, you have 44.1. At 4 second, you have 78.4. And in the 5th second, you have 123 meter. So you see the distance is changing not linearly. So if you look at the pattern, what happens here, the distance actually D, or sometimes we show it with height, okay, H, is basically following a pattern, a formula. And that formula is 1/2 times G, which is the acceleration due to gravity, times T squared. So it's a square of a second of the time. That's what these numbers come from. And this formula was, again, discovered by Galileo. This formula gives you the distance for a free fall. Now notice, the mass of the object doesn't come into this play at all. Doesn't matter how massive it is. It still is going to cover the distance of 1/2 G times T squared. And the velocity is acceleration times T, because we know acceleration G is equal to a V over T, or you can write it like that, V is equal to GT. You may drop a ball with initial velocity rather than let it go. Then you have to just add that initial velocity to this formula, because the final velocity is going to be whatever this velocity is plus that initial velocity. So let's ask this question now. What is the distance covered for free fall starting at rest after 4 seconds? 4 seconds. So distance is equal to 1/2, let's say 10 times 4 squared is 80 meter. If you want to know how velocity and distance are behaving with respect to time, we know that velocity is a linear function. When we talk about a linear function, we know that V is equal to G times T. V, which is function of t, we can sometimes write it like this, V of t, that means V is function of t. Okay, so sometimes you may see it like this. But the distance, which is also function of t, is equal to 1/2 g t squared. T squared, the function parabola, this function shows in this graph. The linear function, V is equal to gt. It shows a linear line in the same graph. So whenever you see a graph like this, if it is a parabola, so you know for the distance, this is a free fall situation. Again, there is no mass showing up in any of these formulas. So it's independent of the mass of the object. Okay, now another question that we should ask is, can an object change in velocity without changing its acceleration? Think about it. The velocity of an object will change, but its acceleration remains the same. Well, if you think about it, when you toss a ball upward, think about what happens to the velocity. The velocity of the ball going up, up, up. So I'm going to toss a ball upward. It's going to go up, 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 up. At one point, is going to stop. So the velocity is going to reduce and stop at one point, and then it's going to come back down, 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 down. Okay. Well, we know acceleration that is affecting this is always g, because that's everywhere. Velocity, it goes up and becomes smaller and smaller and smaller until it goes to v is equal to 0 at this point. So this is v initial, going up. We get to v is equal to 0 at that point. Then the gravity is going to pull it back down, and the velocity is going to increase, becomes bigger and bigger until it comes back to the same location. And this velocity and that velocity are the same value, but the opposite direction. Here's an example for that. So you throw a ball upward, and then it basically comes back down, and you have the same. So you send this up at 13 meters per second. It goes to 0, and then it starts coming back down. And when it reaches here, you have 13 meters per second downward. Here is upward, here is down. All right. But the thing notice here is the value of acceleration is always constant downward because of the gravity. Let's look at realistic situation, which we have the air resistance, air drag. So what happens then? Well, we have a force of drag. So when the object is falling down, the force of gravity, Fg, is always downward, but the force of drag, Fd, it's upward. And you can feel that if you have done it, skydiving, you feel that air force that's pushing you up, and you're pulled down by the gravity. In fact, when you do the skydiving, what happens initially? When you jump from the plane, you are going to accelerate. Speed is going to increase to a certain level. At certain level, your speed is going to be constant. And then you feel comfortable, because initially you feel that your stomach is turning until you get to that point. Now you reach what we call the terminal velocity. And from that point on, you comfortably descend until the point that you have to pull your parachute, otherwise you hit the ground. So you pull the parachute and then you slow down again, a much slower velocity. So let's look at a person or an object coming down from a height. Initially, the force of gravity, Fg, pulling down. Then the force of drag starts building up. So you have small Fd here until this thing comes down some distance, drops down. The force of gravity still stays the same. Fg is the same, but the drag force is increasing now. So in other words, the net force is decreasing until you get to a point that the force of gravity, force of drag, which is opposite, they become equal. And guess what? That means F net is equal to 0 at that point. No more force. No more force, no more acceleration. Up to this point, you were accelerating. Okay? You started initially with the acceleration right after you kind of jumped. You started at initially g, but your acceleration was equal to g, but when you come down, your acceleration is reducing, okay? And it is further reducing until you get here. So A becomes 0. So no more acceleration. And you have a net force is equal to 0. From that point on, you are coming down nicely with a velocity, which call it V terminal, and that's a constant velocity. I don't know if you've done this skydiving. You probably, some of you have done this, you have experienced this. So once you come to that point that now you reach your terminal velocity, you continue that until you get near the Earth's surface, and then you pull your parachute so that you comfortably land on the ground. So air resistance depends on how fast you're coming down and how big you are, or how big is the cross-section surface area. So if you notice, if you want to, when you do skydiving, if you open up your arms and legs and come down flat, you come down slower. But if you make yourself like a straight line and dive, you come down faster. It means it depends on frontal surface area. So let me ask you this question now. When 20 Newton falling object encounters 5 Newton of air resistance, what would be its acceleration of fall? Well, two forces, gravitational force and then air drag force or air resistance force. So 20 minus 5, that would be the net force, right? 20 minus 5 divided by the mass. What is the mass though? Well, when we say it's 20 Newton, F is equal to 20 Newton, we know that is equal to mg. And we know that 20 Newton is equal to m times g, which is 10 meter per second squared. So from here, m is actually 2 kilograms. Now the net force is 20 Newton minus 5 Newton. So that is your F divided by 2 kilogram. And that should give you the acceleration of this object falling. And that comes out to be 7.5 meters. A question now, as a skydiver falls faster and faster through the air, what happens to air resistance force? It actually increases because we just said, air resistance, air drag depends on the speed. If you're going faster, the air resistance is increasing on you. If the skydiver continues to fall faster and faster through the air, the net force is going to actually decrease. So, because at this point, the net force, here, when you get to this point, the net force goes to zero. As the skydiver continues to fall faster and faster through the air, her acceleration, what happens to the acceleration? Well, we just talked about it in this picture right here. The acceleration is going to decrease, starting from G, becomes less and less until it becomes zero. And then it goes down at terminal velocity. Now, the question here is, we have two guys, a big guy and a small guy. They're both jumping to do a skydiving. Which one would hit the ground first? So think about it. All the things that we just talked about and learned, we should apply that. We know that the big guy, so I'm just showing that with a circle. The big guy has a bigger FG. The smaller guy has a smaller FG. When they start coming down, the air drag, we said, is going to act on them. This guy having a bigger FG is going to start accelerating. The air drag now is going to act more on it. It gets down here. When the air drag, force due to gravity, they actually are equal. From that point on, it's going to go with its terminal velocity. Now, this guy is coming down. Its FG is smaller. When he gets to somewhere here, FG and air drag become equal, and it gets to its terminal velocity over there. Now, this guy has accelerated faster to that point, so its terminal velocity, VT, it's bigger than this guy, which reached the terminal velocity sooner. What happens? The big guy is going to build up the higher terminal velocity, and it's going to hit the ground first. So far, we've talked about motion that are in a straight line, and the acceleration is either in the same direction of the motion or in the opposite direction of the motion. If it is the same direction of the motion, the object is speeding up, and if it is in the opposite direction, it's actually slowing down. So we learn all of that. Now, what happens if the direction of the motion changes? For example, in a circular motion, say you have some object that is moving at a circular motion. At this point, its velocity is always tangent to the path. So at this point, although the value or magnitude of the velocity is the same, but notice that the direction is changing. And this object is basically moving around the circular motion. Now, it could be moving in a uniform or constant circular motion. There's a lot of application for that. But because the velocity direction is changing, therefore, there's a change in velocity, therefore we have an acceleration. Now, magnitude could be the same, but if the direction changes, you also have acceleration. We do have acceleration in this case. Which direction is that acceleration? How that affects here? It turns out that acceleration for this uniform circular motion is always perpendicular to the velocity, and it's towards the center of that circle. So these are the acceleration that are changing. Now, the value of acceleration in this uniform circular motion is the same. Magnitude is the same, but the direction is changing. Again, acceleration is a vector quantity, just as velocity. When you have a uniform circular motion, you have velocity changing, acceleration changing, and the direction of acceleration is always towards the center. If this motion is not circle, it could be elliptical or it could be spiral, then the value of these acceleration and speeds can change. We call that a centripetal acceleration. This situation, the object is accelerating towards the center of that circular uniform motion. This is called the centripetal, center-seeking acceleration. Obviously, this object has a mass. Therefore, there must be a force involved here. So the force is equal to mass times acceleration. Now, this acceleration is called centripetal. So we put a little c here and then little c here. So say centripetal force is equal to mass of the object times centripetal acceleration. What is the value of that? Well, it turns out that acceleration is equal to the magnitude of velocity square divided by r. Now, r being the radius of the circle. Now, very, very important point. Suppose this object is tied to a rope, and then you turn this at this uniform circular motion. And then you cut the rope. What happens to the object? At that instant, when you cut the rope, let's say I cut the rope at this instant. I know the velocity at that instant is tangent. Remember, inertia, something that's moving, it wants to move in the same direction. So as soon as this cord is cut, this object is going to start moving in direction of that velocity, tangent to the path. It's not going to go fly outward, contrary to some common, misconception. Okay, this is a subtle point. So now you probably have seen some of these rides in the amusement park. People go in this circular ride, and then they stand on the platform and then lean against the wall. And then this thing starts rotating faster and faster. And then the floor actually drops, but you don't drop down because this is rotating and you're held back against the wall here. So this is an interesting point now. You may ask, wait a minute. I thought you said that this thing is accelerating toward the center, but what's happening here? I feel a push against the wall. Now, you may feel that you're being pushed against the wall here, but that is a kind of a fictitious force. It's really not a force. Just as I brought the example before, when you're holding on the handle in the bus and you're going at constant speed, and suddenly the bus stops and you lean forward. There's no force there. It's only your inertial. Your inertial wants to continue moving at 30 miles per hour. Same thing happens here. This force has a name for it. It's a fictitious force. It's not a real force. It's what we feel, but it's really not. When you feel in the bus, you feel forward as if somebody pushes you forward. Nobody's pushing you. It's just that your inertia wants to continue, go straight. Here, same thing. The inertia of this object wants to go, once it's cut from that circular motion, it wants to go straight. So this is called the centrifugal force. There is an interesting video here that talks about that. Pretty nice video, but it takes some time. In the interest of the time, I'll let you guys watch that on your own. When you feel forced against the wall, and the reaction of your body against that wall is just the support force that you feel. And that same thing happens when you're in your car. Suppose you're going on the highway, and now you have to turn into an exit, semicircle exit. You go turn at some speed, and you feel that you lean the other direction. Why is that? Because now your body wants to go straight because of its inertia. But your car is turning to the side and your body still wants to go straight. So that's why your body tries to do what it's there in terms of its inertia. Force that is actually real here is a centripetal force, because the acceleration, as we mentioned, is equal to v squared over r, the radius of the turn. And that's what we learn from Newton's second law that involves in this situation. There's a force and there's an acceleration. So acceleration due to the centripetal force. And then the passengers are leaning the opposite direction. What they're doing from top, if you look, the passengers want to go straight. They don't want to turn because of their inertia. And that's the first law. And then the third law is also involved here, because now passenger is pushing against the door, and the door is pushing back at you. So the action reaction is there too. So you see how you analyze very simple example in your everyday life. You turn on the exit, you have 3 laws of the Newton applied in that situation. The formulas we already mentioned. It's centripetal acceleration is v squared over r. And from there, you can basically write down the mass times the acceleration. And the mass times acceleration is mass times v squared over r. So if somebody tells you that, hey, I have an object doing a circular uniform path, uniform motion, its mass is m, find me the centripetal force, you say, okay, F centripetal is equal to mass times acceleration, and that's mass times v squared over r. If you give me the radius and the velocity, tangential velocity, they call this tangential velocity, because it's always tangent to the path, then you can find your centripetal force. Now you can see that if you reduce the radius, what happens to the centripetal force? It becomes bigger. If the radius is bigger, the centripetal force becomes smaller. Let's do this example. So we want to find out the magnitude of centripetal acceleration of a car that is going 10 meters per second on the radius of 50 meters. So what are the known values? The velocity of the car, 10 meters per second, the radius, 50 meters, and then use the equation we just learned. Centripetal acceleration is v squared over r. Just plug those numbers in, 10 meters per second squared divided by 50 meters, that gives you 2.0 meters per second. Now, these examples that I do here, these questions that I pose here are important. So make sure if you get it first time, fine. If you don't, go back and review and make sure you thoroughly understand that. You'll see similar to this in the exam. There are other types of force involved, and one is friction force. The mere fact that you can walk on the floor is because of the friction. Now, suppose you were trying to walk on an ice skate ring. You would have a hard time, because as you put your foot and push back on the floor, there's not much of a friction to counter you. And therefore, what happens, you slip. But when you, on the regular surfaces, when you try to walk, you exert a horizontal force towards the back, your force of your feet on the road. And the counter or the reaction force of that is when the floor is pushing you forward. Of course, these other forces are there, but this one has to do with your weight, which is countered or balanced out with the one that is called normal or support force. So these two don't do anything, but this one causes you to move. But if you're in a slippery, no friction, then you won't be able to walk. Now, friction is everywhere. Friction is between the solids, between liquid, between gases or molecules. it's all over the place. And we will see some more examples of that later on. Sometimes we want to have larger friction to increase the friction to avoid slipping. Like, when cold weather, you have a icy road, what you do, you put salt and sand on it to kind of create more friction so the cars won't slip on it. But sometimes you want to reduce that. When you have a ball bearing, you want the wheels to move as easy as possible, or ice skating. And what you put oil in your car for the moving parts to move easier with less friction. So if you zoom in to the interface between objects that are having friction, for example, your hands rubbing against each other, creating friction, you feel the heat. You have rough surfaces that are actually interacting with each other. The molecules of one surface interacting with the molecules of the other. So what you're doing, you're kind of disturbing or displacing some of these surface molecules or atoms. They interact with each other and cause the friction. So in a microscopic sense, that's what happens actually. The smoother you can get these two surfaces, the less of an interaction would be there. So the force of friction can occur, as we just said, with the sliding objects, of course, in the water, in the air, and everywhere. So all of the above. Okay, so when Bill pushes a refrigerator across the kitchen floor at the constant speed, the force of friction between the refrigerator and the floor is, so here's the floor, here's the refrigerator, and you're pushing this. And what happens, this thing is going at constant speed. As soon as you hear that constant speed, you're going to say, there's no net force. So the forces must cancel each other. So if I have a force here, F, that must be equal and opposite to the friction force. So therefore, the friction force must be equal and opposite to the Bill force. So what are different types of friction? Suppose you have your object. Let me see if I can show you this here. And then you have another object sitting on top of this, okay? Now, if I make the angle of this object, you see that the object on top starts moving and starts slipping at a certain angle. When that happens, there are two types of friction involved here. One is the static friction. The static friction basically holds this object as is, no movement. Once it reaches a certain angle, it starts moving. And then we have a kinetic friction when it's sliding. So the static friction is higher than kinetic friction. So it's a little bit harder, we talked about this example, to start having something to move. So you have to apply a little bit more than the friction. Once it starts moving, the kinetic friction is generally less. What is the value of this? Well, if you have an object, obviously the forces that are involved here, one is the force of, say, pushing this way. The other one is the force of friction, okay? And then there are two other forces which we already talked about. We call it Fg and normal force N, which these two are equal. So they cancel. These other forces, if they are not equal, if this force is bigger, this thing starts moving. But what is the amount of that friction force? It turns out that this amount is equal to friction force is equal to some number. That number is called mu times the normal force. Now, normal force, you know, here is equal to Fg, right? And Fg is equal to mass times G. So you can write this in F is equal to mu mg. So that's how you calculate the friction force. You need to know what the mass is, because once you know the mass and you know the acceleration due to gravity, you would know what N is, which is the support force or normal force. And that is equal to times some number gives you the friction force. This number here is a coefficient. It's just a number. Now, this number doesn't have any unit, but we call it a coefficient. And for a static coefficient, we put a S here, mu S, and coefficient of kinetic friction, mu K. If you look at the cases that you have, say, rubber on a concrete, just like, the wheel of the car or bicycle on a road. The static friction coefficient, which is mu S, is 1, but once starts moving, it's less, it's 0.7. Metal on wood is 0.5 for a static, for kinetic is 0.3. A shoe on ice is 0.1, is 0.005. These are some examples that you can see that the static friction is larger than kinetic friction. Another concept that we need to understand and learn here in the case of motion is that when something is moving, which has a mass and also velocity, so we have a car which has a mass m and has a velocity v, and then if you have another car much smaller, it has the same velocity. So what is the difference between these two? If something massive hits a wall, what damage can it do to the wall compared to something that is smaller but with the same velocity hits the wall? What is involved here is a mass and velocity, which basically gives you a momentum. So the product of mass times velocity is called momentum. And we show that with P. So momentum is a property of an object that is moving with a certain velocity and has a certain mass. Now, what is the unit of momentum? Well, unit of mass is kilogram. Unit of velocity is meter per second. So it's kilogram meter per second. That's it. Let's look at a situation here. Let's assume that a boulder is coming down and a guy is trying to run. Assuming they both have the same momentum, that means the product of the mass of the boulder times its velocity is equal to the mass of the guy times its velocity. Will the boulder crush the man? Well, look, the velocity of man is much bigger. So the boulder would never hit the guy because they both have the same momentum. So when a speed of an object is doubled, its momentum, what happens to momentum? So the speed P is equal to mv. So the speed is doubled. So instead of v, we have 2v. The momentum is going to be 2p. It doubles. Simple. The momentum has an interesting property. That means that the momentum of an object or a system will stay the same if there is no external force acting on it. What does that mean? This is the statement of the conservation of momentum. It means that the total momentum of the system before and after an event is going to be the same. Now let's look at some example. A simple example is a cannon and a cannonball. So you have a cannon here, you have a ball inside, and you have powder in there. You fire the powder, explosion happen inside. Applies force inside to both of these. So there is no external, it's internal force now. So what happens here? It pushes the cannon backwards and the cannonball forward. Now, Obviously, the cannonball is going to go much faster because it's smaller mass, but the cannon itself is very massive, so therefore it's going to recoil a little bit, all right? Not much. It means that the momentum of this system stays the same. Momentum of this system here, it was the mass of cannon plus mass of the ball times velocity. That's before. Now, the velocity is 0. It's not moving right now. We haven't fired yet. So this is equal to 0 before. What happens after? Mass of the cannon times velocity of cannon plus mass of the ball times velocity of the ball. Now, a statement of the conservation of momentum tells us that before and after its momentum is conserved because there's no external force, it's all internal. So in other words, I'm saying that mass of the C times VC plus mass of the B times VB is equal to 0. That tells me that the mass of the cannon, which is much bigger, times the velocity of cannon is equal to minus mass of the ball times velocity of the ball. They go different direction. So, or better said, this is minus and this is plus. Another example is that what happens when an object coming from one side hits another object and they stick together. In this case, a big fish eats the little fish. So the big fish coming from the right to left times its velocity, that is before the, eats the little fish. The small fish coming from left to right times its velocity should be equal to after the big fish eats the little fish. Now they are together now. So you add the mass together and they both have now final velocity. So you can find what would be the velocity after that. A lot of examples here. The fact that the jets move forward, so propulsion of the gas and burn, fuel, which comes out from the rocket, causes the rocket to move forward. So total momentum before and after, it should be the same. And all the statements here basically tells you the same thing. Let's look at this example. These two cars, one is a stationary, the other one is coming with 24 meters per second and hits this one. And then they both move at some speed. What is that speed? Now, if these cars have the same mass, they're identical. When this hits the other one, mass of the cart A times the velocity, which is 24.0 meters per second. So this is before, plus 0, because this one, B cart, has a 0, so it doesn't count. This has to be equal to mass of the A plus mass of the B times V final. So look at this. Now, mass of A and mass of B are the same. So let me just put mass here. So I'm going to say M times 24 meters per second is equal to 2M times VF, because M plus M is 2M. So from here, M's drop out, and VF is equal to 24.0 meters per second divided by 2. So it would be 12.0 meters per second. So it would be half. Another concept here is when you apply a force to an object, how you apply the force. Do you do it rapidly, or you just apply the force for a period of time? You take a little bit of a time to apply the force. This concept is called follow through. And for many sports, this is actually used a lot, especially in golf. It depends how you hit the golf ball. If you just hit it abruptly and in a very short period of time, the ball would have a different path and different range than if you hit the ball and follow through. And here, a basketball player, you can throw the ball at a very short, or you can throw it with following through with your hand. You get much better performance. Or when you play the billiard ball, if you hit it in a short time, the ball has a different effect than if you hit and continue hitting it for a certain amount of time. This is important. It's called follow through. And let me show you this example here.
Hi, I'm Piers Ward, and you've joined us at Asprey Hall Golf Club. And in this video, we're going to share with you Jack Nicklaus's secrets on his follow through. You're watching Me and My Golf TV. So in this video, we're going to be talking about what the golf club should be doing through impact. Now, the majority of us out there, we're not really doing a good job with this. So it's really important to get a sensation for what you're after. So I've got Andy in here to help me. So Andy, if you could just take your setup to the golf ball. Now, Jack Nicklaus, so when he says something about the golf swing, we ought to really listen, I suppose. He would say that when the club head was a foot past the golf ball after you've hit it, it needs to be as far away from the left shoulder as possible. So, Andy, can you just go into an impact position for me? Okay, so Andy's in impact. Now, imagine you just hit the golf ball and we're about a foot past the ball there. Now, you'll notice if I were to draw a line from the club head, it's going to go all the way up to his left shoulder. So he's using the full leverage of his body, and this is what we would call a great follow-through position. So the finish is all the way up there. The follow-through is that area there, a foot past the golf ball. Now, it's very, okay, Andy, you can relax there. It's very difficult to sort of say, okay, this is what you need to feel when you hit a golf ball. But if you rehearse that position enough in slow motion and doing what we call deep practice, it will start to replicate and get into your golf game. So Andy, can you just give the viewers a little bit of some examples of some bad and poor follow-through positions?
Yeah, definitely. Yeah. So I suppose the most common follow-through position that we see is where we'd sort of get this sort of flicking pass with the wrist and the breakdown of the hands and arms and even his left arm here. So this is probably one of the most common sort of post-impact positions that we get into.
Yeah, absolutely.
See a lot of people do.
Yeah, and that's all sort of causes all sorts of strange ball flights, particularly high ball flights and poor contact. So again, just if you could just have a few swings for me, just rehearsing that for me. So just actually show the viewers how you would do it as a drill. So you'll notice he's doing this in, that was relatively fast. If we slow that down even more, now the slower he does this, the more his body's going to feel it. And it's going to put a bit of strain on his body. But what it's going to do is going to be rehearsing this great post-impact position.
Okay, I think you get the point, and it makes a difference if you do follow through and if you don't. So if you want, you can watch that on your own. In the interest of time, I'm going to continue. Now, the force that is applied in a certain time is called a delta T. This is called impulse. This is the definition of impulse. Force that is applied on an object in a given time. So it makes a difference. Now, how it makes a difference? Well, it gives a different velocity to that object, just like this golf ball. So if you take more time to apply this force, it would have a different velocity. Therefore, it would have a different momentum. It will relates to change in momentum. The impulse, which is force times T, is equal to change in momentum of an object. So if you have a larger impulse, the change of momentum is going to be larger. That means the mass is not going to change. The only thing that's going to change is because momentum P is equal to mass times V. So delta P is equal to mass times V final minus V initial. Let's say V initial is from 0, so that goes away. So you're only left as mv final. So the more time you take, in other words, you have followed through, your final velocity is going to be larger. So you see how it works? So impulse produces change in momentum. If you want to find out the force, so force times delta t is equal to delta p. So you can just say force is equal to delta p over delta t. And then if you start from rest, so initial velocity is going to be 0. You only left with the final velocity. And when it stops at some point, when final velocity of an object is 0, then it becomes F is equal to P initial divided by the delta P. Basically, this equation tells us that the large time of action, if you have a large time of action, the less is the force on object. So the force on object reduces. Now, let's see how that plays out. Suppose you are running a car and hitting a haystack. Now, haystack blocks you to some extent until you stop. What happens? Momentum here. You have a momentum which has mass times the velocity of your car, and then you stop. Then there's no momentum anymore. Velocity goes to 0. And that is equal to impulse. In this case, the impact time is kind of large because you have to go all through this haystack in order to stop. T in this equation is large. The momentum, so it starts from some velocity, goes to 0. Now, if you hit the same car to a brick wall, what happens? You start with the same velocity and you stop. So the change of momentum is the same. What is changing here is that the time of impact, very short. So what must happen? The force is going to be increased as the time of impact is shorter and shorter. And this is one of the reasons that you see in the highway that when they're doing construction or they put these barrels, they have water in it or they have sand in it. In case you hit those barrels with the car, there won't be as much damage because it takes a longer time. The force is going to be reduced. Force is acting on the car is going to be reduced, and therefore not as much damage to the car or to the passengers. However, if you hit the brick wall, the time is so small and the force is so large, and the damage is going to be devastating. Another type of motion is when you have projectile motion. Now, projectile motion consists of two motion combined. One is the linear motion that we talked about already, linear uniform motion, constant motion. And then linear accelerated, when you simply play a sport and you throw a ball, whether it's a basketball or football or tennis ball, what have you, you're basically producing a projectile motion. This projectile motion allows the ball to go up to a certain height. And now, because of the gravity, it has to come back down to the earth. And the gravity is constantly, it's pulling it down. At any instant, the gravity is always acting on it. Now you can send a ball in a different angle. It so turns out if you shoot the ball or hit the ball at 45 degrees, it covers maximum range. Whereas if you hit it at 75 degrees, it goes higher, but the range is going to be smaller. So this is how the projectile works. As if you shoot the ball horizontally at the constant speed, covers a certain distance at each interval. And then at the same time, you drop the ball vertically, the gravity is going to act on it. and pulls it down, but it's not going to cover the same distance every second. If you add these two, you get a projectile behavior. The path of A is just due to acceleration of gravity that comes down vertically. The path of C is horizontal, uniform, and the B is a combination of the two. You can decompose the projectile motion into two separate motions. One motion goes up and down. Add to it one motion that goes straight horizontal at constant speed. Up and down is acted by gravity, but horizontal is just constant. Now, if there's no air drag, this constant can always at the same speed. But if there's air drag, that affects the speed. And here's the actual vectors of a ball that is set in a projectile. And as you can see, the velocity component starting at some angle theta, the vertical velocity is decreasing, the orange one, until it reaches the top here. But the horizontal velocity stays the same. The x stays the same. And then when it starts coming down, the vertical velocity increases, but still the horizontal velocity is the same until it hits the ground. On all these situations, obviously, gravity is always pulling this thing down. So this is called a projectile motion and has a lot of application. Let me show you a demonstration. Suppose you see a monkey there and you want to throw a banana at him so he can catch it. But you know that as soon as you throw the banana, he's going to let go, he's going to jump down. So which direction should you point or aim the banana? Should you aim it at the monkey on top, or should you aim it at somewhere below so that when the monkey comes down, it catches it? Let's see a demonstration for this. Okay, this demonstration is done at MIT classroom. I used to actually work as a teaching assistant in this room, this particular room. Behind it is a kind of stock room that has all the equipment. I used to set up equipment for a professor when I was a student at MIT. And I did actually set up this setup too at that time. So let's look at it. So we have a little monkey here that is held here on top here by some magnet. And the wire, it comes down here to this little gun that shoots a plastic bullet. And you aim this at a certain point, and then you shoot this, and you notice that the projectile motion of the ball, and at the same time, the monkey is released as soon as the ball is moved from the barrel of this little gun. And you'll see how you have to aim it in order to hit the monkey. So let's do that. So he's putting this little monkey up there, the toy monkey, and it's held by a magnet. And this is the wire you can see that comes all the way down. And he is aiming this little barrel towards the monkey. Now he's aiming directly at the monkey. Notice what happens. Slow motion. He's pointing at the monkey. But what's happening here, both monkey and the ball they both are under the influence of gravity. So if you point at the monkey itself, gravity is going to pull the ball down as well as the monkey down at the same rate. And then when they reach a certain height, they collide. So the answer is you have to point this banana at the monkey in order for it to catch it when it comes down, because both objects are going to come down because of the gravity at the same rate. And that's what happens in that demonstration. We talked about projectile motion, and we talked about the range of this, okay? Now, there's a formula here that gives you what the range is depending on the angle you choose. And again, look, the mass of the ball or object is not in this equation at all. So it all depends on your velocity, initial velocity, and the angle that you hit. And of course, g is the gravitational acceleration. As you can see, the 45 degree would give you the maximum range, because this equation, 45, theta is 45, 2 times theta is 90. Sine of 90 is 1. Sine of 90 has a maximum value of 1. So that times v squared over g, that gives you the maximum range. Of course, if there is air resistance, that changes. So you have to incorporate the air resistance. And we're not going to do that in this course. So the range is going to be lower. Another important law that Newton came with is the universal law of gravity. Gravity, people knew about gravity. What Newton actually discovered, that this gravitational law is universal, is everywhere. Every object would have a gravity. Every object that has a mass, it would have a gravity. The earth has a mass, has a gravity. The apple itself has a mass, has a gravity. You and I have a gravity. He actually came up with a relationship that says that force of gravity between two objects is equal to some number, it's called gravitational constant, mass of the first object times mass of the second object divided by the distance squared. Any object would attract any other object depending on its mass and the distance with respect to the other object. So the reason you see the apple is falling down to earth, because apple and earth are exerting force on each other. Earth is pulling down apple and apple is pulling up earth. But because mass of the apple is so tiny compared to the earth, that's not measurable. So this is the universal gravitational law of Newton. And this G, it can be calculated experimentally. Now, this capital G is different than this little g. Okay, but they're related, but it's totally different. As you can see, the units are different. The unit of this is Newton meter square per kilogram square. The unit of little g is 9.8 meter per second square. When you look at a mass that is attracted by the earth, well, we know the force of gravity is equal to mass times g. And we already said that that's weight of the object. Weight of the object is equal to force of gravity, and that's equal to mass times g. And that force is equal to the gravitational force, which is g, times mass times a big mass, which is the mass of the earth, divided by r squared, which is the radius of earth. Now this m, little m, and this little m goes away. And you're left with g, which is acceleration due to gravity, times capital G, mass of the earth, divided by radius of the earth, square. And that's where the 9.8 meter per second comes from. Universal laws of gravity. Let's do an example. Two objects with mass 1 kilogram and 3 kilogram are 2.5 meter apart. What is the magnitude of gravitational force between them? Well, we know that mass 1 is 1 kilogram, mass 2 is 3 kilogram, the distance is 2.5 meter, and we know the constant, gravitational constant, and we want to find force. You just plug that into this formula, and so we just put the numbers here. G is this, 1 kilogram, M1, 3 kilogram, M2, R2 is 2.5 meters square, and you have 3.3 10 to the minus 11, small attraction force. That forces exist. There is force between everybody, between you and your friend. There's attraction force. Remember, we talked about, weight and force being the same thing, force of gravity. Let's try to see what happens when you feel no weight. Suppose you're in an elevator and the elevator is going up. Initially, you feel a little bit heavier as it accelerates and then goes at constant, especially the older elevators. The new ones are, designed so that you don't really feel that initial acceleration, and then goes at constant speed. And then when it comes down, initially you feel a little bit lighter and then goes at the constant speed. Suppose you have a scale under your feet in an elevator. You can read your weight. Now let's see what happens when, God forbid, the cable of the elevator breaks and the elevator falls down by the gravity and you're falling down by gravity. So you kind of float for a short period of time until you crash. At that short period of time, you feel weightless. Looking at these different scenarios, when the elevator is going at the constant speed, you see your normal weight. But when it's dropping down, temporarily, when it's kind of accelerating down, you feel you're lighter. When it's accelerating upward, you feel heavier. And if the cable breaks, you're floating, but that's weightlessness. That's what happens with astronauts, with people who go up, these guys who went up there for a ride. For a short period of time, they were weightless, they were floating. What happens, and you see this, I think it's Elon Musk here, right? As the aircraft is descending towards the Earth, everything in there is kind of falling down for a short period of time with the same force of gravity, and you're floating, and there's no weight, and that's called weightlessness. And there is a video here that is interesting, so let me show you this.
Have you wondered what it would be like to be an astronaut floating around in the space station? Why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating? No gravity.
No gravity.
Zero gravity.
There's no gravity.
Gravity?
The stuff that holds us to the planet when we spin doesn't happen up there.
Gravity holds you down, so in space there's nothing there. So you just float.
There's no gravity in space.
No gravity, there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So where would the space station fit in this picture? Can you make me a roughly to scale model of the Earth and the moon? And then we're going to position the space station in there. So about like that? Yeah, please.
Close up, maybe. About there.
You ready to see the real distance?
Oh, okay.
It's actually about here, maybe a little further. I think we were wrong. Now, if the moon is here and the Earth is there, whereabouts would you put the space station?
Somewhere here.
About halfway?
Yeah.
Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there.
Oh, okay,
Right
that
there.
close.
Wow.
We're not good at this game.
The space station is actually only about 400 kilometers away. So if you're in Sydney, it's a little further than the drive to Canberra. But does it make sense that the Earth exerts a big gravitational force on you, but nothing on the astronauts just a short distance away? You reckon there'd be no gravity there?
How much they float? We've seen them.
Well, clearly there's not. They're floating around.
I know they float. And the question is why?
No idea. I'm really confused.
Well, in truth, the force on the astronauts is almost as much as the force on you. So then why are they floating while you're stuck here? The answer is the astronauts aren't floating, they're falling. Ah! And not only that, but the space station they're in is falling as well. Ah! So why doesn't the space station come crashing into the Earth? Well, the reason is the space station and astronauts inside have this huge sideways velocity of about 28,000 kilometers per hour. So even though they're falling towards the Earth, they're going so fast that as they fall towards the Earth's surface, it curves away from them. If the Earth didn't put a gravitational force on them, they would fly out into space.
Sure, yeah.
Right? So it's due to that gravitational pull that they can actually keep orbiting the Earth.
If it was to stop moving, it would be plummeting.
Exactly.
But would they?
They would still feel weightless until you smash into something. So the space station and the astronauts inside are constantly accelerating towards the Earth's core, but they never get any closer. And because they're accelerating at the same rate, the astronauts feel weightless. They have this amazing sensation of floating.
The moon is actually falling to the Earth, but because it has a tangential velocity, it constantly orbiting around the Earth. And that same thing happens when you have a satellite or a space station that is orbiting around the Earth with certain tangential velocity. And in fact, that's how we launch a satellite. Now let's assume that you're standing on a tall tower. And then suppose you throw a ball at a very high speed. If the ball has certain speed, it can fall on Earth. But if you increase the speed such that it constantly follows the curvature of the Earth, theoretically, that ball is going to come back and hit the back of your head. Now, what is that speed? That's important. Okay, let's look at it. They launched a satellite with certain speed to put them in orbit. With that speed, it can just follow the curvature of the Earth. Out there is no air drag or anything. So therefore, it can continue going for a very long, long time. Now, what is that speed? Well, it turns out that if you measure the curvature of the Earth, if you go about 8,000 meter or 8 kilometer, the curvature drops 5 meter. The reason for that is obviously the distance that a ball drops in every second is equal to, remember, 1/2 gt squared. So in 1 second, let's see how much an object drops. It's equal to 1/2 g, which is 10, or 9.8. Let me put the unit here. Meter per second squared, times 1 second squared. So this is basically 5. So it drops in 1 second 5 meter. So now, if we throw the ball such that it can go 8,000 meter in 1 second, it would drop 5. So that's the curvature of the Earth. All we have to do to get this object to follow the Earth's curvature we have to give it a velocity of 8,000 meter per second. So that's what we do. We shoot the satellite way up there beyond the atmosphere, okay, about 320 kilometers above the Earth. And then we give it a horizontal velocity at 8,000 meters per second. That way it would maintain the curvature of the Earth. Now, there are other satellites, GPS satellites, you have 3 of them to triangular position of any object. So they send a signal and they receive a signal, and then each one has a certain area coverage, and the intersection of these areas are where that object is. So it would recognize that object, can follow that within very good accuracy. So this is basically the end of chapter 2, which was motion. So have a nice day, and see you guys next time for the chapter 3. Bye.